Okay, I'll jump right in. Thank you for the opportunity to be here. I want to talk primarily about some experiments we've been doing looking at really, really small nanoparticles. We can call them clusters and how they grow, trying to look at individual successive vapor molecule uptake events as best we can. So to motivate this, his name's been mentioned a few times, and I have the privilege of being able to go out for coffee with him once a week. So I poached a slide from Pete McMurray, where this is a field measurement similar to what was spoken about in the plenary session. And what I want to highlight is this nucleation burst event right here, where we have molecules really that are being detected in the sub-nanometer range early in the day, and all of a sudden we have particles forming in this, what was referred to as a banana. And what I want to talk about here is the big question is, what are the key players in this event? Are there methods that we can develop to look at growth in this size scale? And I want to argue that yes, there are. So to talk about that, first we have to say what kind of growth that is. The equations for this have been shown several times, so I do have some slides later about this, but I'll go through them quickly. There's the idea of homogeneous growth, whereas that cluster is composed of a number of molecules, all of which are type A, and another type A comes on, and we have n sub A plus 1, and this would be homogeneous growth. That is most likely almost never what's going on in a lot of environments. What we typically have is NA, and A could be a bunch of different things here, and then a new species comes on B, and we get some sort of heterogeneous species, and then that could proceed with C coming on, and D, and so on and so forth, double A, we can just keep going. And so this appears to be the main mechanism by which clusters grow in pretty much any environment except for those where you're really going out of your way to make homogeneous growth happen. You really have to work to make this happen. Examples, these have been mentioned already: oxidized organic uptake by sulfuric acid amine clusters, water vapor molecule uptake, this would qualify as, and that's what I'll talk about here, and organic vapor uptake in particle detectors, the CPCs we design, are still really heterogeneous uptake at the earliest phases. We're not condensing onto what is the working fluid. So why heterogeneous growth is favored over homogeneous growth? And it's this equation that describes the surface vapor pressure of a small homogeneous droplet. If it applies the Kelvin effect, it doesn't just say there's an energy barrier that's proportional to 1 over r sub c, would be the radius of my cluster. It says there's a huge energy barrier, probably one that's pretty insurmountable unless we get to supersaturations of 3, 4 for these little clusters, 5, 6. That doesn't happen without a lot of work. What's more appropriate is simple binding of individual molecules that could potentially have a much lower energy barrier if it's heterogeneous, or if we had certain complexation. This, of course, gets very material and very complex, and we need methods to look at that on a case-by-case basis, and so that's what I want to present today. So we do this with a device that I was lucky enough to work with as a postdoctoral associate, and Juan de la Mora was kind enough to help me get set up in my own lab. It's a differential mobility analyzer mass spectrometer. This is P5 stands for prototype 5. This was developed in Juan Fernandez de la Mora's laboratory, originally by a student named Juan Roos, and others have worked on it. And it's a parallel plate DMA. Resolving power was mentioned this morning. I was telling Juan last night that on a good day we get a resolving power above 60, on a medium day a resolving power in the 50s. So we're able to see very small changes in mobility. This mass spectrometer is coupled nicely this differential mobility analyzer is coupled nicely to a mass spectrometer. And so we can get exact chemical composition because we have a nice high resolution. And so what we do to look at uptake, you can imagine, is if we have a cluster, this is a small sub-nanometer or around a nanometer entity, and we bring it into this DMA, we can get its mobility, and then we can get its mass. Then what we can start to do is we can introduce a vapor that we're interested in looking at the uptake of in very controlled conditions, subsaturated. And so we can control the saturation ratio of the sheath flow. We can do this with a variety of vapors. I'll show our preliminary measurements are with water, which is one of the easiest things to work with in the lab. And we can look at shifts in the mobility. And we can look at really, really subtle shifts. In fact, 1% we can detect the shift of, because we're not trying to resolve that peak with anything else. We're just looking at a small shift. And in this way, we can actually look at individual vapor molecule uptake events. We can look at transient binding. That is, if something sticks for a little while and comes off, it will shift the mobility enough for us to pick up on it. And so that's what we've tried to do, and we've tried to develop a theory for analyzing these data. So over here, what I'm showing, just to make clear what we're looking at, is this is the type of data you get out. These are electrosprayed iodide salt clusters, so sodium iodide, potassium iodide. We tend to use these in our base experiments simply because they're easy to make, and the spectra are some that we're pretty good at interpreting. We've transformed mass to charge ratio here into the number of cation anion pairs here, so this would be metal iodide N. And Z here is the charge state, and here's the voltage on the DMA, which is proportional to inverse mobility. These little line segments you see here, therefore, respond to a cluster of a specific chemical composition and a very specific mobility. The width of this line segment is defined by the resolution of the instrument. The signal intensity here is out in a log scale, so really where the signal is just a little dot in the middle of all of those. You can isolate things very easily by charge state when you look at this plot, so you can see the singly charged, the doubly charged. Things like dissociation events, which were spoken about in the plenary session. If things break apart in the mass spectrometer, what you would see, for example, here, we have this peak, and we see a peak at the exact same mobility, but it's one cation anion pair below. That is a phantom peak brought about by dissociation. And so we can account for all of these events. Basically, you can interpret the spectra. So we can get at the mobility of things whose chemical composition we know exactly, and then you can watch that mobility shift as a function of saturation ratio of whatever you dope the system with. These are what data look like as we increase the saturation ratio. The base data I'll show today will be these iodide salt clusters, which we just have a lot of experience with. That's why we worked with them, with water. So these are 3 different cluster ions that we're looking at the mobility spectra of. So we've isolated them for a given mass. This is the dry spectrum. And then we've slowly increased the saturation ratio. The highest saturation ratios we go up to are about 0.6 to avoid condensation anywhere in other lines where we might have cooling. And what you can see, of course, is a shift in the inverse mobility, which suggests that things are getting bigger. And so you can try and quantify that. We quantify it not in terms of the mobility, but working with the mobility equation and not assuming that things are a sphere in terms of what's called the collision cross-section or first collision integral. It has units of meters squared, SI units. It's proportional in a lot of instances, but certainly not equal to the projected area. So we can think of it as a size quantifier. If I was to work with traditional growth factors, the growth factor would simply be the collision cross-section measured at saturation ratio S divided by the baseline collision cross-section to the 1/2 power. So this ratio that I'm going to report is related to the growth factor. So we can look at this now on an individual scale. Here's the saturation ratio of water. These are different cluster ions, and we're isolating them by their molecular composition. You can certainly see that, yes, the collision cross-section increases. As water is uptaken, it increases appreciably. In some cases, we can get up to about 40%. 40% for the M equals 9 clusters. And we can see very different behavior for different materials. For example, in this particular case, sodium iodide appears to not uptake a lot of water at small cluster sizes, but uptakes more than anything else at large cluster sizes. Conversely, cesium shows very little uptake overall, but actually even decreasing uptake as size increases. There also appears to be some clusters, the N equals 9 clusters uptake more water, and it's unanticipated, but we see very chemistry-specific, structure-specific, and size-specific behavior down at this scale. So then, of course, you need a way of quantifying this or relating this to theories. If you assume, and this is a safe assumption for water, not for everything, but certainly for water, that the ions equilibrate with the background surroundings in the DMA, you can relate the shift in collision cross-section to the equilibrium binding coefficients of successive water vapor molecules. So J water vapor molecules, J+1 water vapor molecules, as well as the collision cross-section you would expect specifically with a certain number of water vapor molecules bound. So during the measurement, as the ion traverses the DMA, it doesn't always have the same number of vapor molecules bound, sometimes 2, sometimes 3, sometimes 4, but it probes the equilibrium distribution. So you can link it to the binding coefficients as well as the collision cross-sections with specific numbers of water vapor molecules bound. To get at the collision cross-section ratios here, we use computational chemistry approaches, which have been put into a software package developed by Carlos Lariba, who's now at Indiana University, Purdue University, starting up his own lab. Here we're looking at, these are his computations. You can simply email Carlos and he gives this code away freely. He just likes to know who has it in case someone has any issues with it, he can help out. And what you're looking at here is gas molecule scattering off the surface of a dimethylamine sulfuric acid cluster ion. This particular structure with water vapor molecules came from Murray Johnston's group, who we collaborate with. And what's being calculated here is the collision cross-section orientationally averaged through looking at momentum transfer from this gas molecule to this specific cluster ion. And so we can get these collision cross-section ratios, and they go into inputs into our calculations. They look something like this. What you can see is, so here's this number of water vapor molecules bound to different clusters. Here's the relative shift in collision cross-section we see. We're starting to see, when you get up to 20 water vapor molecules bound, shifts on the order of what we see in experiments. So then we have to put it all together. So what these experiments then enable in the end is predictions of the equilibrium binding coefficients. This prediction can come from anywhere. It can come from computational chemistry, which would be ideal. We've predicted these. Do they directly agree with measurements? We hope so. If not, we can iterate. And then you can compare it to other models. So we did a classical model comparison. This would be Kelvin-Thomson route, where we tried to fit a surface tension as well as an activity coefficient, give it two free parameters and see how well it does. And then just for comparison, I would never argue that this is the way the universe works. Why not do a Langmuir absorption model with an activity coefficient and a maximum number of binding sites built in? Don't treat this as a nucleation problem, but just a direct binding problem. See how you do. So what I want to show is that the classical prediction, even with these two free parameters, the concavity of these curves does not look like anything we ever see in experiments. We just can't best fit it. The idea of applying classical theory to heterogeneous processes down here just doesn't really mesh well with what we observe for different clusters. We can fit part of the curve, but then it just always has this very high uptake that's predicted when you have a low activity coefficient built in that you just don't see experimentally in the initial stages of uptake. Meanwhile, again, I'm not arguing for this model. We were surprised how well we can fit every data set we've ever had with a Langmuir absorption curve. We can get pretty much the whole saturation ratio range, every ion, very little variation for the most part. And so we can parameterize on a case-by-case basis the extent of heterogeneous uptake on the molecular scale. Those types of curves maybe don't give some ideal on how much water is being bound. We can do a collision cross-section weighted average. So this is, the clusters travel through the mobility under this saturation ratio with the same mobility approximately as something, say, with 4 water vapor molecules bound here. And so what you can see in this particular case, these are different number of clusters, is that the amount of water, again, is certainly material dependent. It's very cluster specific, and it doesn't increase monotonically or decrease monotonically with the number of cation anion pairs. And so we need to treat each cluster as its own special little entity that behaves differently than things smaller than it, larger than it, or with different chemical composition. But we can do this. We can actually probe this chemistry. So I have some summary and conclusions and then some perspective on future prospects along this. So the DMAMS instrument that Juan has put together is just really excellent in that it allows these types of measurements to go on, that you can get high resolution mobility measurements and monitor those shifts is really, really useful. For the most part, this can be applied to any cluster, if you can make it, and any vapor molecule combination, provided you can let the ions be in the DMA long enough to reach an equilibrium. This becomes an issue. It's an interesting issue for things of low vapor pressure, but then you get into a kinetic regime where you can actually probe kinetics of uptake. Measurements to date that we see strongly suggest that classical predictions really never agree well with data over a wide range. You can fit a narrow range, but then you just get deviation, even when you have free parameters in the fit. So where do we see this measurement going? If we look into the aerosol literature, at least what I see a lot of is I'll see a lot of field measurements, certainly a lot of large chamber lab scale reactor studies, which are trying to get at atmospherically relevant conditions. And then you'll also see comparison to quantum or first principles calculation. And what I want to argue is this type of measurement, which I would call controlled laboratory measurement, it's not trying to simulate what's in the atmosphere. It assumes we can get a stable cluster source and then look at how that behaves, where you don't necessarily need atmospherically relevant conditions. The idea of the Gibbs free energy change isn't dependent on necessarily where things are, other than to say the temperature. We can get at a lot of these quantities through these types of measurements. And I think it should serve as the buffer between these moving forward. That is, you take this, which provides information for this, which you can then directly compare to this. Going from here to here requires a lot of fit parameters. These are very complicated experiments. We should take information of them and go into the controlled laboratory setting before we compare to theory. Other ways that you can do this. So what we're doing is a form of ion mobility spectrometry, mass spectrometry. The key, why did I work with iodide clusters first? It's because we need methods to produce clusters identical to those found in these laboratory studies. The iodide clusters aren't special for any reason other than that they are really easy to produce repeatably. And so if I'm doing base calibration experiments to say I can look at water uptake on the molecular scale, why not work with these? Of course, along with that, we need to be able to produce controlled amounts of growth of compounds of interest. Sometimes figuring out what those compounds of interest is hard enough as it is, but the next step is then can we actually generate that in controlled quantities to look at how it binds. I compare right now to bulk theories and very simple theories. We need quantum chemical calculations to give us equilibrium binding coefficients for direct comparisons. This is where I think we're going. We, of course, can only go up to saturation ratios less than 1. I really can't look at supersaturation out of fear of complete and total growth to micrometer sizes. But these types of experiments can be coupled with expansion chamber experiments. These have been done by the Vienna group, Paul Winkler and Paul Wagner et al. We do low saturation ratios, and they can do these really nice, beautiful measurements at high saturation ratios. And then, of course, the idea of getting away from mass analysis, IMS coupled with spectroscopy, if we can get enough signal, I would think would have a lot of potential to probe the chemistry of chemically identified species. And that is my last slide, so thank you very much.